This is going to be a quick recap of all the lessons we've had with bonding, which corresponds with Chapter 6 in your textbook. This is concerned with the way in which atoms form compounds. In one of our first lessons, we used the periodic table of electronegativities, found on the back of your periodic table, to figure out what the difference in electronegativity was between the bond of two atoms. And there's a range of these differences that will give us a clue about what type of bond. If it's 1.7 to 4, we can predict that to be an ionic bond. If it's 0.3 or below, we can predict that to be a nonpolar covalent bond. And in the middle, those are polar covalent bonds. Covalent bonds form between nonmetals, such as carbon and oxygen, or fluorine and fluorine. Ionic bonds form between metals and nonmetals, an element from the left of the periodic table bonded to an element from the right side of the periodic table. And then third, metallic bonding occurs between atoms of the same type of metal, which accounts for the properties of that metal. Here's an example. Looking at the bond between carbon and nitrogen, the electronegativities are 2.5 to 3.0. That's a difference of 0.5. We take the absolute value of this. According to that chart, this makes this a polar covalent bond, meaning part of the molecule is going to have a partial negative charge, and the other part will have a partial positive. We look to see what type of oxidation number these elements would have to determine where the partial positive and negative would fall. So the polar covalent types of bonds, the PC bonds, we show the partial charge. We show the PC. Practice drawing the little sigmas so that on the test you can draw this correctly. On Friday we did an activity using the little colored discs to show the valent electrons and the shared bonds that form, the covalent bonds that form between nonmetals. In this example, not all of the electrons around the chlorine are shown. However, the electrons showing the bonds are shown. Since carbon has 4 electrons, and each chlorine has 7, with there being 4 of those halogens, each of the 4 valence electrons of carbon can satisfy the octet for all 4 of those halogens, forming the covalently bonded CCl4. Here's a similar molecule from the activity that we actually did. You'll notice on this one, it does show most of the valence electrons. Looks like I may have run out of dots. Hold on. There we go. Now all the fluorines have the complete octet of electrons. So all of these atoms are satisfied by sharing the electrons that form the bond between each carbon and fluorine. We can see that everybody's enjoying an octet of electrons. The last lesson we had on bonding was about ionic bonding. These bonds form between metals and nonmetals. In this example, we have the metal of calcium that has 2 valent electrons, and iodine, which has 7 valence electrons. It will take 2 iodines to have enough places to accept both of calcium's valence electrons. Therefore, the chemical formula is CaI2, because there's 1 calcium and 2 iodines. We use the red arrows to demonstrate the transfer of the electrons from the metal cation to the nonmetal anion. With these structures, there are different notations. Single bonds represent 1 pair of shared electrons. By these examples, both C and D exhibit single bonds. A double bond will be 2 lines. That would be 2 pairs of shared electrons. Structure B in these examples is exhibiting a double bond. And then finally a triple bond, drawn with 3 lines, is 3 pairs of shared electrons, and our structure A here has a triple bond. Of the ones that have only 1 pair of unshared electrons, that would be B and D. Not C, because C actually has 2 pairs of unshared electrons, and that doesn't answer the question. The last question asks, what effect do unpaired electrons in the central atom have on a molecule? These unpaired electrons cause the molecule to be polar. They make a molecule polar. Our lesson on polarity, we used the special dipole arrow A dipole arrow has the little mark at the end of it. And we use these to point from low electronegativity toward the element with a high electronegativity. And when that creates a symmetrical pattern, those are said to be nonpolar. But when it's imbalanced, then it is polar. Any unshared electrons, like the ones I've circled in red, automatically make a molecule polar. For molecules that are polar, we show the partial positive and partial negative charge, considering what the normal oxidation would be for that element determines whether it's positive or negative. Unpaired electrons automatically make that end of the molecule partial negative. Now for the review section. All of this stuff will be on the final exam. That's why I've continually reviewed with you throughout the year so that it's not a shocker. Questions 32 and 33 on your study guide talked about electron configuration. That was chapter 4, where we read the periodic table from left to right, methodically going through the blocks S, P, D, and F, and the energy levels, 1, 2, 3, 4, 5, 6, and 7. So on this one, we're looking for phosphorus. Phosphorus is found on the third row. It's a nonmetal, so it's on the right-hand side of the periodic table, and it happens to be the third one over in the P block. So this is its electron configuration. As an ion, phosphorus will pick up 3 additional electrons, thus the charge of -3. And when it does that, it then has the same configuration as the element argon, which is a noble gas. There's a question about good lab safety habits. I know that you're familiar with good lab safety habits at this point, so just list a few. The rules for significant digits will not go away. The rules of significant digits will apply to every calculation done in chemistry until May 25th. This question is specifically asking about the rule when numbers are multiplied. For example, if I have a number like 2.1 times 3.55 times 6, I have to consider how many significant digits are in each of these numbers. This one has 2 significant digits, this one has 3, and this one has 1. So when I give my answer, that answer will have to be rounded to 1 significant digit because my data has the least significant as 1 significant digit. In 36, you're just counting the number of significant digits. If you've forgotten, remember your box and dot. You start at the first 1 through 9 digit to the last 1 through 9 digit, and you box those in. Anything trapped in the middle counts. On the second one, it's only the 4. If there's a decimal, then you would consider anything that's to the right of the last number, not the right of the decimal. Nobody cares where the decimal is. It's to the right of the last number. The blocks on the periodic table correspond with different shapes of electron orbitals. The S block has a sphere-shaped orbital. P is dumbbell-shaped, D 4-lobe-shaped, and F are funky-shaped. In 38, I give you a set of elements. I just want you to look on the periodic table and tell me which family these are. Sodium, lithium, and potassium are the very first family. Those are the alkali metals. Helium, neon, argon, xenon, those are the last family. Those are the noble gases. To the left of that are the halogens, including fluorine, chlorine, bromine, and iodine. And the metals copper, silver, and nickel are all found in the D block, which are all transition metals. And then there's the dreaded conversion problem, which you need to show by dimensional analysis. Start with the given information, and then show how you're going to use a conversion factor to take it to the base unit of liter, and then from the base unit liter to the desired unit of milliliter. Always remember there's more than one way to do things, right? So if instead of 10 to the 9 liters per gigaliter, you could say that 1 liter is 10 to the -9 gigaliters. I know, I keep using giga, and I keep forgetting we didn't even learn giga. We stopped at mega, but that's okay. I'm telling you now, giga's 9, and I don't think it's that one on the test anyway. And then for the other one, milliliter, we could always say that 1,000 milliliters make 1 liter. When you do the math, it comes out to the same answer anyway. And then on the second example, we're going from centimeters to meters and then meters to kilometers. Going from prefix to prefix will always be a three-step problem. Once you figure out each conversion factor, like how many centimeters in a meter, how many meters in a kilometer, you're going to multiply across the top, divide across the bottom. The end. All right, go back through your other worksheets, go back through chapter 6, review the study guide, and do well on your test tomorrow.